Hello, this is Captain Steve Tarrant from Maine Maritime Academy with another NS301 stability video. In this one we're going to be looking at freshwater and dock water allowances. The story in this case really starts with specific gravity. Specific gravity is based on a cubic centimeter. 1 cubic centimeter freshwater weighs 1 gram. 1 cubic centimeter salt water weighs 1.025 grams. You can see that the salt water is a little heavier, and that's due to the salt dissolved in the water. Well, specific gravity is defined as the weight of a cubic centimeter of a substance divided by the weight of a cubic centimeter of fresh water. So in this case, the specific gravity of salt water is 1.025 grams divided by 1 gram. You can see that the grams cancel out, and so you get this absolute value 1.025. Now, this is a useful number because we can compare the specific gravity of salt water to, let's say, the specific gravity of something else, and then we can get an idea of the relative densities of these various items compared to water. How do we measure specific gravity on the ship? Well, when you're loading your vessel, you're going to, you're going to basically get a sample of that water that's around the ship, and you'll put this brass hydrometer in there, and it's calibrated for specific gravity, and then you can get the density of the water where you're actually loading. Now this is important because different densities of water are going to create different water lines on the vessel. For instance, let's say that you are in freshwater, okay, and you loaded the vessel to this level here. Well, that's a specific gravity of 1. Well, if you immediately just transported the vessel into salt water, specific gravity 1.025, the vessel would rise on its own. The reason being that that salt water is heavier and it would push the boat up. So, fresh water, this water line, without adjusting the weight of the ship at all, just changing the water that it's in, the vessel would rise. This is called the freshwater allowance. It turns out that when all ships are designed to be loaded to what's called the design water line, okay, in this case, this is the salt water line. Really, you're not supposed to surpass that in most conditions because you need what's called freeboard for reserve buoyancy, okay? You get out there and you're in bad weather, the ship's going to be rolling, and you need that freeboard, that reserve buoyancy, in order for the ship to be able to right itself. The other thing is that let's say you take damage to the ship, you take a hole and a compartment floods, well, that's going to sink the ship as well. So you need that reserve buoyancy, that freeboard, in order to keep the ship safe. But if you were to be in freshwater, and you load your vessel to this design water line, by the time you get out into the open ocean, the ship's going to rise, so you wouldn't be carrying enough cargo. So we have this freshwater allowance, which we're going to look at in greater detail in the next couple of slides. By the way, the freshwater allowance can be found in the capacity plan, which most vessels will have. And it's a nice schematic of the ship, various levels, the tanks, capacities, your deadweight scale, and lots of stability information. So, freshwater and dock water allowances. So if you loaded a vessel in salt water to a certain loading condition, its water line might be here. Now, if you put that vessel into freshwater, the load line, the water line the ship would sink deeper, and you'd have a new water line up here without changing the weight of the vessel at all. Just by going from fresh to salt or salt to fresh, okay, you'd have a different water line. And the difference between that water line at a specific gravity of 1, fresh water, specific gravity 1.025, salt water, is the freshwater allowance. And you can express that in inches, centimeters, okay? Well, it turns out that each vessel has its own freshwater allowance because it's based on the shape of the vessel. Now, what's the likelihood that you're going to be someplace where the specific gravity is exactly 1? Not very likely. Okay? you're likely to be in some specific gravity greater than 1, perhaps less than 1.025 if you're loading in some port. You'd be in what's called brackish water. Okay, so let's say that the salinity was halfway between 1 fresh water and 1.025 average ocean water. Well, where would the water line be? Well, you may have already figured it out. That specific gravity is halfway between 1 and 1.025. So if we were in 1.012, this is where the water line would be. And if we then went to C and got out into 1.025, the vessel would rise from this level to this level. So that's what we refer to as a dock water allowance. Okay, it's the allowance made for the actual salinity of the water at the dock. And in this case, because the specific gravity is halfway between fresh and salt, our dock water allowance would be half of whatever that freshwater allowance was. So you'd be allowed to load half of that freshwater allowance. Okay, now here's another way of looking at it. This is the same vessel loaded the same exact way in each condition. However, the only thing that's changed, the variable that's changing, is the specific gravity. Okay, over here, this would be a specific gravity of 1. This would be a specific gravity of 1.006, 1.012. The water is getting saltier as we go to the average salinity of seawater itself. Well, now what we're going to do is we're just going to project all these various water lines over to this one, and we're going to compare some stuff. So the question really is going to become, if there's a freshwater allowance for this vessel, how much would we be able to use here, here, and here? So I'm just going to project that water line from freshwater all the way over here. This is our freshwater allowance, the difference between 1 and 1.025. All right, and it has some value, centimeters, inches. It's dependent upon each vessel that has a different hull type, has a different freshwater allowance. Well, now if we project this one over, you can see that that salinity is 3/4. 1.06 is just a little bit. It's just a little bit saltier. It's a quarter of the way from 1 to 1.025. Okay, well. You can see that as a result of that, we can use 3/4 of the freshwater allowance. The dock water allowance is 3/4 of the freshwater allowance. Well, how about here? This one here, this is halfway between 1 and 1.025. Okay, well, we would be able to use half of it. And here, all right, this salinity here, this density, is 3/4 of the way from 1 to 1.025. Which means we'd only have a quarter of our freshwater allowance left. That would be our dock water allowance. And of course, if we were in 1.025, there'd be no allowance because we're at 1.025. Now there's a formula for this. And the formula has all these terms. It's basically figuring out the ratio. So the dock water allowance is equal to the freshwater allowance times specific gravity of salt water minus specific gravity of dock water divided by the specific gravity of salt water minus specific gravity of fresh water. My goodness. Turns out that we already know some of these values. We're going to be able to look up the freshwater allowance from our capacity plan. The specific gravity of salt water we already know is 1.025 on average. The specific gravity of the dock water we're going to measure with our hydrometer. The specific gravity of salt water again is 1.025 and fresh water is 1.000. So we can actually take this now, substitute some terms in there, and this is the formula that you should probably actually memorize. All right, so 1.025, whatever that value is from the hydrometer, and then 1.025 minus 1 gives 0.025. And so that's an introduction to freshwater allowance and dock water allowance. The next thing we're going to do is look at load lines and load zones and then put it all together.